Hello students, welcome back to yet another session in unit number 4. In this session, we are going to discuss about thermodynamic wet bulb temperature. In earlier session, we have seen what is wet bulb temperature, and now we are going to see its thermodynamic properties. So these are the topics we have completed in unit number 4. And now we are going to see thermodynamic wet bulb temperature. So this topic we shall cover today, and in next session we will see psychrometric of air conditioning processes, mixing of air streams. So these are the three other topics we have to see in this unit that we will see in coming 3 more classes. So thermodynamic wet bulb temperature, or it is also called as temperature of adiabatic saturation. So both ways you can call this. And suppose if you are getting question in university question paper, what is thermodynamic temperature of the adiabatic saturation, you have to answer the same thermodynamic wet bulb temperature. So that is the title. You have to be little careful. And for any state of unsaturated moist air, there exists temperature T star at which the air becomes adiabatically saturated. So here at this temperature, and air becomes adiabatically saturated at this particular temperature by the evaporation of water into air at exactly the same temperature T star. So without changing the star, so it is happening at T star itself, and figure shows the schematic process. I will show you the diagram. It is referred to as adiabatic saturation process. It is also called as adiabatic saturation process, and whatever may be the title or name, you have to be a little careful and you have to do this. The leaving air is saturated at temperature T star, and the specific humidity increases from omega to omega star, and the enthalpy is also increased from H to H star. The weight of water added per kg of dry air is omega star minus omega. So that is nothing but the weight of water added in this particular context, and it adds energy to moist air. The enthalpy added in similar way, omega star minus omega into H dash W, where H dash W is the specific enthalpy of water rejected at the same temperature T star. So this is the diagram, and this is the inlet. Inlet air is coming into this chamber, and feed water is given here, and now this becomes T omega and H. So at inlet we have T omega and H. At the outlet we have T star, omega star and H star. And for the heat rejection is calculated, or heat added is calculated, T minus H, the T and H, T star and H star, HI star. Now that can be calculated is equal to omega star minus omega, that is per kg of dA, that is dry air. And this is the adiabatic enclosure or adiabatic chamber where there is no heat transfer takes place. So this is the this figure is known as adiabatic saturator, and feed water is rejected into unsaturated air, inlet air at T, and leaving air is saturated at T star with increased omega and H star. Mass and energy are conserved over the control volume. So mass and energy are conserved over the control volume. So that is the final conclusion from this. And now from this diagram you can conclude these 3 points. So energy balance, so that is equal to H plus omega star minus omega into H dash W, that is equal to H star. and where H equal to CPT plus omega HV, and H star is equal to CPA T star plus omega star HV star. So, and HV star is equal to HF star plus HFG star, enthalpy of saturated vapor at T star. So its derivation is very simple, and by substituting all these terms into the above equation, that becomes HPT plus omega HF star plus HFG star uh, plus omega star minus omega H dash W. So that is equal to CPT star plus omega star HF star plus HFG star HFG. So simplifying the same equation, the Cp plus omega Cpv into T minus Cp plus omega star Cpv into T star, that is equal to H star Fg into omega star minus omega. So now we can assume that Cp equal to Cpa, that is also equal to Cpv. Still we can simplify this with this assumption, and Cpt minus T star equal to Hfg star into omega star minus omega. So that is equal to T star equal to T minus Hfg star by Cp into omega star minus omega. So now we can see these two differences, so T dash and T star, and comparing both expressions, wet bulb temperature T dash equal to T minus K omega by Fg into H of G dash into omega dash minus omega. So thermodynamic wet bulb temperature T star becomes T minus H star Fg divided by Cp and omega star minus omega. So now very similar to this equation. So this is the differences. This is the difference in equations between T dash and T star. So Lewis number and its equivalence, if we see, and if Fg divided by k omega Cp equal to the Lewis number, that is equal to 1, so that becomes T dash equal to T star. So when Lewis number and its equivalence considered, in this case T dash will become T star, where Le is the Lewis number, a dimensionless quantity, and for air vapor mixer at low pressure, Le equal to 1. So now we can consider this Le equal to 1 Lewis number, and the actual value of Lewis number is equal to 0.945, and which is dimensionless. So from here you can conclude this. So T dash equal to T star if Lewis number is unity. Please remember this. And hence the measurable wet bulb temperature is numerically equal to the thermodynamic wet bulb temperature. So in this case, when T dash equal to T star, in this case the measurable wet bulb temperature is numerically equal to thermodynamic wet bulb temperature. So however, this is valid only for air water vapor mixers. So for water vapor mixers, air water vapor mixers, it is applicable. For other gases, the vapor systems, T dash is not equal to T star. So this is very important point you should remember. And though T dash and T star are equal in psychrometrics, they are conceptually different by this way. And now measurement of psychrometric properties. It may be seen that there is no convenient way of directly measuring these quantities, like specific humidity, that is omega, degree of saturation, that is nu, and relative humidity pi. So there must be calculated from measurable parameters only. So these must be calculated from measurable parameters. There is no direct measurement, And the directly measurable psychrometric properties are dry bulb temperature, that is T, and wet bulb temperature, that is T dash, and dew point temperature TD. So these three can be directly measured from psychrometric properties. Why three points are needed? Why these 3 points are needed? So that is a good question to ask here at this context. To completely define the thermodynamic state of the air water vapor mixer, three independent properties are needed. They are, so total pressure P, so that is nothing but barometric pressure, and dry bulb temperature, that is T, and third property is either wet bulb temperature or dry bulb temperature. So that is dew point temperature. dpt is dew point temperature or wet bulb temperature. These three are essentially needed to measure the thermodynamic state of the air water vapor mixer. So it is these three are very much essential. So dew point temperature measurement, it is measured by cooling a bulb in an air stream until dew appears. So dew is nothing but the droplets that actually accumulates on the surface of any surface of any wall, and when this dew appears, the dew point measurement can be measured, and the corresponding saturation pressure of water is equal to partial pressure of vapor PV in the air, and it is difficult to accurately measure dpt due to precision issues. Wet bulb temperature measurement, measured with a psychrometer. So wick covered bulb is rotated at 160 to 660 rpm in air, and though wet bulb temperature is not thermodynamic property, it is easily measurable and hence very useful also. So in problems also it is very much useful property. And the thermodynamic connection here, while no analytical relation exists between WBT, that is wet bulb temperature, and PV from first principles, as WBT, wet bulb temperature, the true thermodynamic property, and now it coincides with the temperature of adiabatic saturation temperature. So that is nothing but T star. So this T star is known as adiabatic saturation temperature, and that's what we have seen in earlier slides. Hence, WBT can be treated as a thermodynamic property and used to determine PV. So that is the WBT is a thermodynamic property, and this is was very much essential to determine the PV. So empirical relations to estimate PV from wet bulb temperature. So suppose if we measure wet bulb temperature, so from here how to estimate or how to calculate PV. So these are the equations we require, and this is the modified Upjohn equation. So this is known as Upjohn equation. So PV equal to PV dash minus 1.8 P into T minus T dash divided by 2700, and where the PV dash equal to saturation pressure at wet bulb temperature T dash, and P is barometric pressure. So next is another equation to calculate this or estimate the PV, that is modified Ferrel equation. So this is PV equal to PV dash minus 0.00066 P into T minus T dash, that is multiplied by 1 plus 18T divided by 1571. So next another equation we have, that is carrier equation. So that is PV equal to PV dash minus P minus PV dash divided by 2800 minus 1.3 T plus 32 into 1 T minus T dash into 1.8. So this is the carrier equation. So by all these three equations, we can calculate PV. So please remember all these three equations. All temperatures T dash are in degrees Celsius, and PV dash is the saturation pressure of water at T dash, All pressures may be in any consistent unit, so it can be Newton per meter square, or it can be of Hg, or it can be in terms of atmospheric pressure. So to conclude this, and we can see here these empirical equations allow the estimation of partial pressures of water vapor using easily measurable wet bulb temperature. So once we know wet bulb temperature, we can estimate the partial pressure. And despite its non-thermodynamic nature, WBT, wet bulb temperature, remains an essential practical loop in analyzing the thermodynamic analysis and air conditioning design. So this is another important property we should always remember, and with which we can calculate the partial pressure also. So one simple example we can see here. The problem statement: calculate relative humidity, humidity ratio, dew point temperature, density, enthalpy of atmospheric air when the dBT equal to 35 degrees Celsius, WBT equal to 23 degrees Celsius, and the barometric pressure is also given, that is 750 millimeter of Hg. Now the first one, relative humidity. So from saturation properties of water, so saturation pressure at WBT, so that is wet bulb temperature T dash equal to 23 degrees Celsius, that is given. So from that PV dash can be can be found out from the tables, that is 21.06 mm of Hg. And using carrier equation, so here we can directly apply carrier equation. So PV equal to PV dash minus P minus PV dash into T minus T dash into 1.8 divided by 2800 minus 1.3 into T plus 32. So carrier equation, when we substitute all these values, and all these values now we know, and we can easily calculate PV. So that is equal to 15.18 millimeter of Hg. So from steam tables at 35 degree Celsius dBT, dry bulb temperature. So PS is from tables, it is 42.4 mm of Hg. So now pi can be calculated. Pi, that is relative humidity, can be calculated. So that is equal to PV by PS into 100. So that is 15.18 divided by 42.4 into 100. So that is exactly 36%. So next one, humidity ratio, specific humidity or humidity ratio are one and the same. Already we have seen this, and now we can find out omega. So omega equal to 0.622 into PV by P minus PV. So that is by substituting PV and P. So we are getting this 0.1285 kg of water vapor per kg of dry air. So this is what we are getting here, omega. And dew point temperature TD from steam tables. So all of you carry steam tables to the exam. And saturation temperature at PV equal to 15.18 mm Hg pressure TD. So TD is equal to 17.7 degrees Celsius. So densities, the dry air, P rho A equal to PA by RAT. So that is equal to, by substituting all these values, we are getting 1.1086 kg per meter cube. So that is the rho A density of dry air. And water vapor, so that is rho V equal to, that also we can calculate by substituting the values. Now we know all these values. So now we get this 0.0143 kg per meter cube. So that is the water vapor density. So total moist air equal to rho A plus rho V. So that is equal to 1.1086 plus 0.0143. So that is equal to 1.1229 kg per meter cube. So enthalpy of moist air. So H equal to 1.005 T plus omega 2500 plus 1.88 T. So with this equation we can find out the H value. So that is 1.005 into 35 plus 0.01285 into 2500 plus 1.88 into 35. So by calculating this, we are getting 68.15 kilojoules per kg of dry air. So that is the problem, and the problems will be very similar to this problem only, and the simple problems. Please remember the equations to solve very easily, and also use uh, practice well how to use the steam tables, and it will be very handy to start this. And now students, coming to reference books, please refer the CP Aurora. This is the good book for this topic, and you can refer other books, R.S. Kurmi, Rajput also, for additional problems if you wanted to solve. So these are the references, and we stop here, and in next session we shall see psychrometric chart. So how to use psychrometric chart and what are the properties of it, that we are going to discuss in next session. We stop here. Thank you students. We meet again in next session. We stop here students.